And I'll be posting these up on Schoology later as well in a PDF format. So if you if you want to just sit back and do that, that's fine. But it would probably be a good idea to jot down a couple things as we go. So the first question: imagine a place in the cosmos far from all gravitational and frictional influences. So you're way out there in outer space, way out there. Suppose that you visit that place and throw a rock. The rock will gradually stop or continue in motion in the same direction at constant speed. Please, I hope you get it all right. Hang on. Now you can answer. Let me move it to the other side. No, that's not what I wanted. All right, that's question 1. How about question 2? A 2-kilogram object is moving horizontally. No glasses, Luke? Well, move up. 2-kilogram object is moving horizontally with a speed of 4 meters per second. How much net force is required to keep this object moving at this speed and in this direction? You can round off to no decimal places. Type in a number. 2-kilogram object moving with a speed of 4 meters per second. How much net force is required to keep this object moving at this speed and in this direction? Enter a number, please. Question number 3 states, Mac and Tosh
I get it.
are arguing in the cafeteria. Mac says that if he flings the jello with a greater speed, it will have a greater inertia. Tosh argues that inertia does not depend upon speed, but rather upon mass. Who do you agree with? And you're going to have to explain why.
Why?
Well, you just enter your answer, but then I might call on someone later. So, Mac is the one that says if he flings the jello with a greater speed, it has a greater inertia. And Tosh says it depends upon the mass. By the way, don't fling jello in the cafeteria. Okay, moving on. Number 4. Suppose you were in space in a weightless environment. You're way out there in space again. Would it require a force to set an object in motion? I'm way out in space. I have my chapstick in my hand. Would I need a force to get it moving? Not a problem. My friend Fred spends most Sunday afternoons at rest on the sofa watching pro football games and consuming large quantities of food. There's a picture of him right there. What? There's not even a joke there. I'm not always funny, you know. What effect, if any, does this practice have upon his inertia? Does it increase Fred's inertia? Does it decrease his inertia? Or no, it has no effect whatsoever on his inertia. Because inertia depends upon speed, right? Question number 6. Bend too close.
I get it.
Thank you. It's being chased through the woods by a bull moose which he was attempting to photograph. The enormous mass of the bull moose is extremely intimidating. Yet if Ben makes a zigzag pattern through the woods, he'll be able to use the large mass of the moose to his own advantage. Explain this in terms of inertia and Newton's first law of motion. So how do we explain this? The moose has more mass, so he has less inertia, so he's not able to make the zigzags as easy. The moose has more mass, so he has more inertia, so he's not able to make the zigzags as easy. Or C, it will not work. The moose is still able to make a zigzag pattern. Oh yeah, physically. Physically. And actually. Same thing. Question number 7. 2 bricks are resting on the edge of a lab table. Surely she's short.
I don't get it.
Stands on her toes and spots the 2 bricks. She acquires an intense desire to know which of the 2 bricks are most massive. Since Shirley is vertically challenged, she is unable to reach high enough and lift the bricks. She can, however, reach high enough to give the bricks a push. Discuss how the process of pushing the bricks will allow Shirley to determine which of the 2 bricks is most massive. What difference will Shirley observe, and how can this observation lead to the necessary conclusion? So, is it the brick that moves more, has more inertia, and is heavier? the brick that moves less has less inertia and is lighter, or both bricks feel the same and move the same distance.
They're both
I
I don't know, are they two identical bricks?
Let's say 2 bricks are resting on the edge of a lab table. Well, I will say select the best edge. Okay? So the brick that moves more has more inertia and heavier, so like if it's bigger, right, it'll have more inertia, so she can, it'll keep moving more. Or the brick that moves more has less inertia and it's lighter.
Wouldn't if it's heavier, it would move less?
Well,
But there's more friction on the thing.
then that you're saying B, the brick that moves more has less inertia and is lighter,
Oh, okay.
right?
Oh, yeah.
Question number 8. Look out below.
Nah.
Drops an approximately 5 kilogram fat cat, weight of approximately 50 newtons, off the roof of his house in the swimming pool below. Please do not do this. This is a trained stunt cat. Connor, take your butt out. Upon encountering the pool, the cat encounters a 50 Newton upward resistance force, which is assumed to be constant. So the cat weighs 50 newtons, gravity pulls down with 50 newtons, he hits the water, and then there's 50 newtons of buoyant force pushing up.
You'll stop.
Use this description to answer the following questions.
So is the water like flat or what? Or like kind of weird?
It's flat water.
Okay.
No, it's horizontal. It's gonna get harder. It's horizontal.
So it
Yeah.
might kill a cat.
He's a fat cat, he's good. Which one of the velocity time graphs best describes the motion of the cat? These are velocity time graphs. They are graphs of the velocity. Which one is correct? A, B, or C?
I gotta read the question.
Same cat. Which one of the following dot diagrams best describes the motion of the falling cat from the time that they are dropped to the time that they hit the bottom of the pool? The arrows in the diagram represent the point at which the cat hits the water. So, do the dot diagrams, would it be A, this is the water here, water there, water there. Which one of those is most accurate? I'll maybe zoom in a bit, they're a bit small. Can I do this? Can I just make that picture bigger? Yeah.
So if you use that like the same distance?
I would say these are the same distance, and then I would say these are getting close together, right? Several of Luke's friends were watching the motion of the falling cat, because who doesn't love dropping fat cats off roofs and pools and inviting their friends over? Being physics types, much like yourselves, they began discussing the motion and made the following comments. Indicate whether each of the comments are correct or incorrect. So, friend number 1 said, once the cat hits the water, the forces are balanced and the cat will stop.
Yeah.
Let's try and do these last ones quicker. We got to get to 13. So number 11, upon hitting the water, the cat will accelerate upwards because the water applies an upward force.
So are you talking like that? Like as soon as they hit water bouncing, or are you talking like it's kind of
Will accelerate upwards.
That means like gaining.
Boing.
That's
yeah, I get from like a bouncing point, so I'm gonna put that.
the water's not going.
So say false. It should be easy then, right? Are you?
Yeah, does it have a little bit of time to like move down? Like,
Upon hitting the water,
Sounds like right in the spot.
the cat will accelerate upwards.
Right in the spot.
Yes.
This lady almost
Upon hitting the water, the cat will bounce upwards due to the upward force.
On the water?
Upon hitting the water, the cat will bounce upwards.
Last one didn't say bouncing.
Yeah, I'm confused about number 1 now.
Yeah, me too. I think you explained
Is
it
it
wrong.
like on the water?
I didn't explain nothing. I just kept reading the question over and over again. Tried to.
Well, let me consider that.
I never you said the word bounce, ever. Should we play it back? Last one, 13. This one is the Big Daddy one.
Okay,
If the forces acting upon an object are balanced, then the object must not be moving with a constant velocity, must not be accelerating, or none of these. I'll let you read it again.
you go back to 11.